You walk out of the exam room feeling like an absolute genius. A week later, you realize a single missing unit and one tiny, prematurely rounded number just nuked an entire grade boundary. Yeah, it is brutal. And it happens to thousands of Cambridge IGCSE physics candidates every single year. So today, in this explainer, we're literally reverse engineering top band answers, making sure you never, ever hand over those easy marks again.
Okay, let's dive into this right away. Look at the difference here. A classic, painful 2 out of 10 answer looks exactly like this. Density is mass and volume. Mass went up, right? This is exactly why ordinary revision completely fails. You might vaguely get the physics, but you're just not speaking the examiner's language. Now contrast that with the 9 out of 10 answer. It correctly states the formula, rho equals m over v, and explicitly calls out the mechanical failure. Volume was rounded prematurely to 2 significant figures, causing a cascading error. Missing your units or rounding too early will absolutely destroy a density calculation because honestly, the examiner just can't award method marks if your intermediate steps are a total mathematical mess.
And, the data totally backs this up. A staggering 45% of lost marks come down to missing units. Another 35%, early rounding, and 20% are just vague, non-scientific explanations. Think about what that means. 80% of the time, students aren't losing marks because they don't know the physics. They're dropping grade boundaries purely because of sloppy exam technique. It's painful.
But hey, we are fixing that right now. To actually beat the mark scheme, you need a bulletproof strategy. A reliable system that literally guarantees you hit every single requirement the examiner is actively looking for the second you put your pen to paper.
And this brilliantly illustrates what I call the 4-step answer framework. Step 1 is the concept. Always state the relevant law or equation first. Step 2 is evidence or data. This is where you plug your numbers into that equation or quote specific data from a graph. Step 3 is scientific reasoning. Explain exactly what happens and why it happens, relying purely on physics principles. And finally, Step 4, examiner wording. Use the exact, precise terminology they use in past paper mark schemes. Honestly, this is a highly scalable framework for reverse engineering perfect Cambridge answers every time.
So let's take this exact framework and actually apply it to a classic Cambridge-style mass and density problem. Imagine a practical investigation where we're measuring the mass and volume of a liquid to figure out its density.
Now, what's really interesting about this experimental data is how the variables scale. We've got mass in grams and volume in cubic centimeters. Trial 1 gives us 50.0 grams and 12.4 cubic centimeters. Trial 2 jumps to 75.0 grams and 18.0 cubic centimeters. And then Trial 3 hits 100.0 grams and 25.0 cubic centimeters. I want you to look really closely at these numbers.
Actually, let's make this interactive. Take a second and just think about it. Can you spot the anomaly in this practical investigation? Look at the relationship between the mass and the volume as we move across those 3 trials. Something in this specific data set is completely flawed. Do you see it?
In just a moment, I'll show you the exact examiner clue that flips a 0-mark pressure calculation into full marks. But first, you need the framework that makes identifying anomalies completely obvious.
All right, did you catch it? The anomaly was sitting right there in Trial 3. If you calculate the density for the first 2 trials, it comes out to roughly 4 grams per cubic centimeter, right? But Trial 3 lands on exactly 4.0, whereas the others are just a tiny bit messy. In a real Cambridge practical, perfectly clean data is a massive red flag. It usually points to human error in reading the instruments. So, to fix this and secure those top band marks, you have to suggest specific practical improvements. Always tell the examiner you would repeat the readings and calculate an average. Make sure you mention checking for a 0 error on the mass balance before you even start. And this is crucial, specify that the volume must be read from the measuring cylinder at eye level to avoid parallax error.
Okay, let's seriously escalate the stakes here. We're moving away from simple density and diving into a much harder higher mark topic that blends forces and mechanics. Get ready for an interactive challenge on resultant force.
Let's nail down the concept first. The resultant force is formally defined as the single force that has the exact same effect as 2 or more forces acting together on an object. But listen closely, because this is where candidates constantly drop marks. Resultant force is a vector quantity. That means your final answer absolutely, non-negotiably, requires both a magnitude, so the number and the unit, and a specific direction.
So, the crucial point is seeing where this goes wrong. A perfectly flawed answer simply says, the resultant force is 15 newtons. Sure, they get a mark for the math,
but they completely lose out on the top band. Now the exam-safe, top-tier answer states the resultant force is 15 newtons to the right, causing the object to accelerate, and naturally references F equals ma. This answer does it all. It hits the magnitude, the unit, the direction, and provides the scientific reasoning for what that force is actually doing to the object.
And while we're on the subject of forces, we have to talk about the most fatal flaw in the entire syllabus, 9.8. Burn this number into your brain. The gravitational field strength, lowercase g, is 9.8 newtons per kilogram here on Earth. One of the most absolutely devastating ways to lose marks in these calculations is confusing mass, which is measured in kilograms, with weight, which is measured in newtons. Remember, weight is a force. Mass is just the amount of matter. So, if a question gives you a mass of 10 kilograms resting on a surface, the downward force is not 10. It's 10 multiplied by 9.8. Forgetting that distinction? Yeah, that is gravity's revenge on your final grade.
But don't just take my word for it. This is straight from the source. The Cambridge Examiner reports explicitly state, and I quote, "Many candidates lose marks by confusing mass with weight, failing to state the direction of the resultant force, or omitting final units." Validating your own learning process against what the examiner is literally complaining about year after year, that is an incredibly effective strategy. If they hate it when you forget the direction, your new obsession needs to be writing down that direction.
All right, now it is finally time to resolve that open loop I mentioned earlier. Let's move to Wazelli and see how this builds into tackling the most notorious trap in the entire Cambridge syllabus, the infamous zero-mark pressure calculation. Let's walk through the steps for pressure and see how our 4-step framework saves the day. Step 1, identify the force. Usually this means you're calculating weight, where W equals mg. Step 2, calculate the cross-sectional area. Then step 3, and please pay attention because this is the exact trap examiners set. You absolutely must convert that area from square centimeters into square meters before you calculate the pressure. If you plug square centimeters directly into the pressure formula, you get 0 method marks for the final answer, none. Finally, step 4, calculate the pressure using P equals F over A.
To really cement this high-mark strategy into your brain, I want you to run every single calculation you finish through this rapid final answer checklist. Did you explicitly state the correct formula? Check. Did you actually show the examiner the exact values you substituted into it? Check. Is your final answer rounded to the correct significant figures, which is usually 2 or 3? And finally, the big one. Did you include the correct unit, like pascals or newtons per square meter?
If you stick to that checklist, you are going to completely stop bleeding marks on your calculations. You've got the physics concepts locked in, and you've mastered the mathematical framework. But here's the catch. Your absolute perfect answer still depends on one final, incredibly critical detail. Because knowing all this physics simply isn't enough if you fundamentally misunderstand the command word at the very start of the question. If they ask you to explain and you just describe, you get 0 marks. All that brilliant physics knowledge is completely wasted. Decoding these command words is the mandatory next step if you want to secure those top bands. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Because next time, we're figuring out, are you answering the question they actually wrote or just the one you hoped they would ask?